Welcome to today's lecture. So in our lecture notes we will today treat section 5.3 on the real spectrum of polynomial rings. So we already in section 3.6 we actually did already some work into that direction. So we actually related, maybe in the easiest case it was just that we were looking at the polynomial ring in n variables over the reals, and we wanted to relate its real spectrum somehow to R2n, right? And in fact, in section 3.6, the setup was a little bit more general, and it was, so the exact setup is a bit technical. So let's see what was exactly the setup. Yeah, so we had a preordered ring, and that's a commutative ring together with a preorder, and in fact it was soon specialized more. So we had actually we started with an ordered field K together with less than or equal, and then we looked at its real closure R, and we took n variables x1 up to xn, and A was the polynomial ring over K in these n variables. And when we looked at this preorder, so we made this into a preordered ring by looking at the preorder which is generated by the non-negative elements of K. And then AT was a preordered ring, and we were looking at the real spectrum of AT. Right? And so effectively we are looking at the elements of a real spectrum of this polynomial ring over this ordered field that contain all the non-negative elements of the ordered field, so that they respect the order of the ordered field, right? And when we, why did we look at this real closure? Because we wanted to relate the real spectrum of this preordered ring to the elements of R to the n, where R is this real closure. When we had certain results, and maybe for the most relevant was with slimming. So we looked at the constructible sets of AT. So, you know, just in the last lecture we defined the constructible topology. It was generated by certain sets. And the same generators, if you take the same generators, but now you let them generate a Boolean algebra, right? Then you get this, the elements of this Boolean algebra are called the constructible sets. On the other hand, I looked at the K semialgebraic subsets, K semialgebraic subsets of R2n, right? And yes, and I had this slimming, which mapped the constructible set into this semialgebraic, K semialgebraic set. And then we had also and that was an isomorphism of Boolean algebras, and we had also the inverse map, namely the fattening, right? So now that was a very indirect way of relating, well, in the easiest case, R to the n to this real spectrum, right? because you were just talking about these Boolean algebras. So in this easy case, it would be here just semi-algebraic subsets of R to Vn, and here were constructible subsets of this real spectrum here. Now we want to make this connection a little bit more explicit, so it will still be not satisfying, but maybe that's not possible. The real spectrum is not so easy to understand, but we want to understand it much more when we did last time. Okay, good. So we will also use the topologies that we had introduced last time. And now we are going to the topic of today. So we are here. The real spectrum of polynomial rings. So exactly as in section 3.6, we fix in this section an ordered field k less than or equal, and we denote by R its real closure. We let n be a non-negative integer, that's the number of variables, A is the polynomial ring over k in n variables, and T is this pre-order generated by the non-negative elements of k. Moreover, we denote by curly S a Boolean algebra of all k semi-algebraic subsets of R to Vn. And by C, the Boolean algebra of all constructible subsets of the real spectrum of AT. Consider again the isomorphisms of Boolean algebras, namely the slimming from C to S. So that was that you take a constructible set and you just look, every point in R to Vn we had learned gives rise to a prime cone, namely Px. That's just all polynomials over k which are non-negative at x. And I just map this constructible subset of real spectrum to a set of all x in R to Vn such that the corresponding prime cone Px lies in C. Okay, so nothing easier than that. But that's actually an isomorphism of Boolean algebras, which was non-trivial, right? That needed a lot of theory. And the fattening is just the inverse operation. It's also an isomorphism of Boolean algebras, of course. And now we can interpret the fattening in terms of in topological terms. So let S be a k semi-algebraic subset of R to Vn. When the fattening of S is the closure, right, in the topological sense, of this set of all Px, x in S, in the real spectrum of AT. And important with respect to the constructible topology. Okay, and maybe there is now, one can get easily a bit confused now, so maybe it doesn't get more confusing if I explain it. So I had introduced a constructible topology on the real spectrum of A. I did not introduce it on the real spectrum of AT, but I think it's clear what I mean. The induced topology, of course, because the real spectrum of AT is a subset of the real spectrum of A, and I mean that I look at the induced topology. Okay, so maybe I even make a reminder on induced topology, so subspace topology. So if I have a topological space M, and I have a subset N. When the subspace topology on N was defined as follows, so a subset B of N was open in N if and only if there exists a subset A of M such that A is open in M and B equals the intersection of A with N. Okay, and but the same thing when it's of course closed for we have the same thing for closed subsets, right? That would be an equivalent characterization of a subspace topology that it satisfies some subset is closed where that means it's a complement of an open set if and only if there is a closed subset of M such that B is the intersection of that subset with N. Okay, how do you, yeah, that's easy to prove, right? So, you know, it's just playing around with complements. You can do it immediately, but you shouldn't forget on that. So, so what are now, you know, because of 5 to 8, the real spectrum of AT is closed in the real spectrum of A. With respect to the, well, actually with respect to both topologies, the spectral one and the constructible one, but for us now constructible one is relevant, right? So we are using now real spectrum of AT is closed in the real spectrum of A with respect to a constructible topology. That's what we use now. And therefore, you see immediately that the closed subsets. So if I have B here, when B is closed, if and only if, I mean in the real spectrum of AT, if and only if it is closed in the real spectrum of A, right? Because, you know, if it's an intersection of a closed subset of real spectrum of A with real spectrum of AT, when it's actually closed when it is actually closed in the real spectrum of A, because because an intersection of closed sets is closed, since that set is closed in the real spectrum of A. Yeah, so, and you know, that would be true for both the constructible and the spectral topologies, but what I needed for the constructible topology now. And therefore, okay, and therefore if I have a subset of real spectrum of AT, which I have here, when it is actually, when it's closure, you know, that's its closure in the real spectrum of A and in the real spectrum of AT is the same, right? Because it's easy to see, right? Because I mean, closure in the real spectrum of A can be at most this, because this is already closed. Closure is the smallest closed superset, and yeah, and when you see it by this here. Okay, so so that was hopefully not too confusing, but I think with technical details one should speak about. Okay. Okay, so why is now to a statement? So why is the fattening with closure? For the duration of this proof, we endow a real spectrum of AT with a constructible topology. So if you don't say anything, we mean now the constructible topology as while normally we would mean the spectral topology. So since the complement of the fattening of S, you know, the fattening, we know, of course, it's a constructible set, and its complement is therefore also constructible, and it is open in a constructible topology simply because it is constructible. I mean, the constructible topology is one generated by constructible sets. And now maybe again confusing a little bit. Originally we had the constructible sets, subsets of a real spectrum of A. And now, okay, but when, again, very easy to see that the induced topology here is in fact generated by the constructible subsets of a real spectrum of AT, right? With little subtle points which maybe you would not even have noticed if I didn't mention it, and maybe I don't confuse you too much. Hopefully I don't confuse you too much, and maybe I'm overcomplicating some things also. But yes, so this complement of a fattening of S is of course constructible, and therefore it's open in the real spectrum of AT. And the fattening of S is therefore closed with respect to a constructible topology on the real spectrum of AT. So S is the slimming of a fattening of S, because these two are inverse to each other, and and by definition this is the set of all x in R to the n such that prime cone Px lies in the fattening of S. We have in particular that for every x in S, Px lies in the fattening of S, and that gives one of the inclusions we have to prove, namely, because the fattening of S is closed, I can take on the left side the closure, and I'm still contained here. So the closure of the prime cones Px with x and S, of a set of these prime cones, is contained in the fattening of S. And that's already one inclusion of the equality we are claiming, namely we are claiming that fattening of S is actually the closure, so we have to prove the other inclusion. So in order to show the other inclusion here, we let P be an element of a fattening of S, and we are taking a neighborhood of P in the real spectrum of AT with respect to a constructible topology. And we have to show that this neighborhood intersects the set of all Px x in S. I used just the, we had this description of a closure of a set in a topological space, right? That's what I'm using here. So we have to show that U intersects this. And of course I can again assume that U is actually an open neighborhood. And because the fattening of S is open, and P is an element of a fattening of S, I could further intersect without loss of generality. I mean, I could replace U, the open neighborhood U, by its intersection with a fattening of S, which is again open. So that means I can assume actually, I can suppose actually that the U is contained in the fattening of S. Now, so U is an open in the constructible topology, and the constructible topology is generated by the constructible sets. And so every open set with respect to the constructible topology is a union of finite intersections of constructible sets, but finite intersections of constructible sets are constructible. So, and in fact, the open sets in the constructible topology are just the unions of constructible sets, right? So we can further, so by writing U as such a union, there must one of these constructible sets contributing to this union must still be a neighborhood of P, must contain P, and therefore be a neighborhood of P. And this and that's of course still is contained in the fattening of S, even more contained maybe, and yes, and if you can show for that constructible set that the intersection with this set is non-empty, when we are done. So that means we can, without loss of generality, we can assume that U is actually constructible, right? And by 362, we know how our constructible subsets look like. Where is it? Here, right? They look like this. And so I can actually write it here in that way also. And then I have that U is of this form here, where F and VGI are polynomials over K. So since Slim is an isomorphism of Boolean algebras by 364, it follows that follows from the fact that U is non-empty and contained in the fattening of S, that the empty set is not the slimming of U, you're right, because I'm dealing with an isomorphism of Boolean algebras that does not map that maps a non-empty set to a non-empty set. Slimming of U is non-empty, and that's contained in a slimming of fattening of S, right? Because it's preserving the inclusion, of course. And then this is equal to S. So yes, so remember we wanted to show that U intersected with set is non-empty. Maybe let's color this to show what's this. Okay. Taking into account that the slimming of U is actually this here, if you think about it. There is thus an X in S, since the empty set is not equal to U, is not equal to the slimming of U, there is an X in S satisfying this. And this translates into f head of px equals 0, g1 head of px greater than 0, and so on. And thus px lies in U. So it was a quite technical proof, not really hard. You could have done it yourself, I think, after some time of figuring out. And so we have this topological description of a fattening of S using the constructible topology, which is still a bit of a strange topology. Okay, so now we draw a corollary. So the set of all px, so these prime counts attached attached to the points x in Rn, associated to its points in R to the n, lies dense in the real spectrum of IT with respect to the constructible topology, right? So they are so that's really a contribution to saying that the real spectrum is closely related to R to the n, right? Because in some sense R to the n is a dense subset of it, right? With respect to the constructible topology, which is a bit of a strange topology, but also with respect to a more natural spectral topology, right? And you know, if you have a non-empty open set in a spectral topology, it's a non-empty open set in a constructible topology, of course. And therefore, it suffices to show everything for the constructible topology. So that's a bit of a stronger statement. And why is it true? Well, let's look at this thing here. So this is actually the so it's closure. Its closure is by the previous theorem, the fattening of R to the n, right? And since the fattening is an isomorphism of Boolean algebras, this is of course the real spectrum of AT. So that means this lies dense. Okay, fine. So that's undoubtedly another close relationship between R to the n and this real spectrum. But let's go on and let's try to find out what are really the elements of this real spectrum. We won't get really an explicit description like we have in one variable. In one variable we have, in some cases at least, for example, if, maybe that was the only example in the lecture, the real spectrum of this, if x is just one variable, we have a really nice description, you know. I mean, the picture I've drawn so many times now. For each real number, we have exactly 3 elements in the real spectrum. And when we have 2 additional ones at minus infinity and infinity. Okay, so such a nice description we won't get in the case of several variables. So we will not have a full understanding, but we will have a better understanding what are really the elements of a real spectrum. And this has to do with ultrafilters in the algebra of k-semialgebraic subsets of R to the n. Right, and so that's why we speak now about these filters and ultrafilters. Let curly f be a filter. Let curly f be a filter in this Boolean algebra S of k-semialgebraic subsets of R to the n. Then I can take all filter sets, all elements of a filter, and look at their fattenings. And then if I collect all these fattenings, that's again a filter, but this time in the Boolean algebra of constructible subsets of a real spectrum of AT. And if I intersect all these sets in this new filter, then I get a non-empty set. Okay. On the other hand, if f is even an ultrafilter in S, then this set of all fattenings of elements of f is even an ultrafilter in this Boolean algebra of constructible subsets of real spectrum of AT. And this intersection of all elements in the filter is then even a singleton. Okay? So yeah, so this looks like already like you know, a singleton. So that means the only element, of course, when is a point in the real spectrum of AT. So that yeah, here you can already guess that an ultrafilter in S, yeah, you see already that it gives rise to a prime cone, right? And the converse will also be true. But that's for the next lemma. Okay, so the first part follows immediately from the fact that that fattening is an isomorphism of Boolean algebras. If you think about the definition of a filter, respectively an ultrafilter. So yeah, so this is meant with the first part, of course, right? So right, that's what we mean with the first part. So yeah, let's you know, look at the definition of a filter and ultrafilter in a Boolean algebra. So this definition was here. So if S is a Boolean algebra on a set, when a subset is called a filter, if it satisfies these axioms, right? And ultrafilter if it satisfies in addition that axiom. And you see easily by definition of an isomorphism of Boolean algebras. Maybe let's see this. So so it was here in 191. Homomorphism of Boolean algebras was this, and isomorphism was a bijective one, right? And so of course such an homomorphism of Boolean algebras is monotonous. So you know that phi of if S and T here in the first Boolean algebra satisfy S is contained in T, when phi of S is contained in phi of T. That's an important thing to note here, maybe, right? Why is this? Okay, that's just because S contained in T is equivalent to S equals S intersected T, and from this it follows that phi of S equals phi of S equals phi of S intersected phi of T, and that implies that phi of S is contained in phi of T. And then for an isomorphism of Boolean algebras, we have in fact an if and only if here, right? And yes, and so from this you see that all the properties of a filter are preserved. It's quite easy to see. Okay, let's maybe once more look at the definition of a filter. You see everything very easily. So the thing with the inclusion that I just mentioned is in order to see that this property is preserved, right? So yeah, so in this case, so that means the first part is almost trivial, right? And now the second part about the intersection of all these fattenings. Okay, so for each S in the filter F, fattening of S is closed with respect to a constructible topology, right? We know this already. So that was because it's, for example, because it's constructible. I mean, you could also use this because it's the closure of something. But an easy argument is because it's constructible, and each constructible set is of course closed with respect to constructible topology because its complement is constructible and therefore open. Okay, it would follow from the it would, so in case, so it's proved by contradiction. So if you assume the contrary of what we want to prove, namely that this intersection is empty, right? Then together with the compactness of real spectrum of AT with respect to constructible topology, which we have remarked that was here, right? So real spectrum of AT is compact with respect to constructible topology, and that closed subsets of compact topological spaces are compact. Okay. So it would follow that where so this is an empty intersection of closed sets in a compact space, right? That means the union of the complements is everything in a compact space, and the complements are open, right? So that's so from this you get an open cover of a whole space spare AT, and but this is compact, already quasi-compact would be enough. So there is a finite sub cover, and that translates into a finite intersection of such things which are already, which is already empty. So there would be a positive integer n, and S1 up to Sn in a filter F, such that already this finite intersection is empty, which would imply that the fattening of intersections of ESI is empty, right? Simply because this is the same thing as this, right? Because fattening is a homomorphism of Boolean algebras. And thus, since fattening is, since the fattenings, since by definition of, so now I can apply the slimming, which is inverse to a fattening, and since this is a homomorphism of Boolean algebras, it maps the empty set to the empty set, and so I get the empty set equals this finite intersection, but this finite intersection is in the filter, okay? Finite intersection of filter sets is in the filter, but it would be empty. The empty set cannot be an element of a filter by definition of a filter, so we have a contradiction, right? Okay. So we have now proven that this intersection is non-empty. Now in case of an ultrafilter, so let F be an ultrafilter, and then of course this filter is also an ultrafilter, and suppose we have two elements in this intersection, and assume that they are not the same points in the real spectrum, when we need a contradiction. But the real spectrum of IT is a Hausdorff space with respect to a constructible topology, right? We had said it's compact, so in particular it's a Hausdorff space. So there is some C in C such that, so is there some, some neighborhood, and I can take an open neighborhood of P. Yeah, I mean, I don't use the full force of Hausdorff, right? But so Hausdorff would say there are disjoint neighborhoods of P and Q. Actually, here I'm just taking a neighborhood of P which does not contain Q. And if I can take an open neighborhood, but an open neighborhood is a union of constructible sets. So I can actually take a constructible set that contains P as an element, but not Q. And since this is an ultrafilter in the Boolean algebra of constructible subsets of real spectrum of IT, we obtain that C is in this filter, in this ultrafilter, or the complement of C. So one of C or complement of C is in this ultrafilter I've just highlighted here in orange. And so that means C or complement of C is of form fattening of S for some S in the filter F. So in the first case, it follows that Q is not in the fattening of S, right? Which would be a contradiction, because Q was supposed to be in all fattenings of all filter sets of F. In the second, it follows that P is not in there, which is also a contradiction, right? So this, so in both cases we have a contradiction. So this assumption here must have been wrong. So P equals Q. Okay, so this lemma gives us now the possibility to get from an ultrafilter in the Boolean algebra of k-semialgebraic subsets of R to n an element of a real spectrum, right? Yes, and so actually we know already if U is an ultrafilter in S, when the intersection over all with fattenings is a singleton, right? Okay, so that was already this here, right? And now what we want to do in this lemma, we want to describe the singleton a little more, okay? So we want to describe the element of this singleton a little more. So we claim actually that this is the set of all, so that this prime con P associated to the ultrafilter U is in this Boolean algebra of k-semialgebraic subsets of R to n is the set of all F in A. You know, A was a polynomial ring in n variables, so okay, such that the set of all x in R to n, where f of x is non-negative, right? So that's the set where f is non-negative, where this polynomial is non-negative, is a filter set, okay? And, the idea is that you are saying that something belongs to its prime cone, right? If and only if some polynomial, if and only if its non-negativity set, and here I have to take it in R to n, is in the filter, okay? So that's a pretty nice way to get from an ultrafilter in this Boolean algebra a prime cone. So yes, so let's maybe make an example. So if I take again the case where we know already much about the real spectrum, if you have just one variable, so I take a polynomial ring over the reals in one variable, so that's the easiest case. The easiest case that is of interest. And now I know how the k-semialgebraic subsets of R to the n. So I take k equal R. So I look at a Boolean algebra of all semialgebraic subsets, right? Boolean algebra of all semialgebraic subsets of R. I think you know how this looks like, right? So this is these are unions of finite unions of intervals. It consists exactly of finite unions of intervals, right? And now I need an ultrafilter on this. And yes, so let's see. One ultrafilter. Maybe I make I can make 2 examples. One ultrafilter would be given by. So if I take. Let me take here a real number. Let's take, for example, 3, and then I can take the ultra. So maybe let me make several examples. The first example, U1, would be the set of all S in the Boolean algebra S, so finite unions of intervals S, such that 3 is contained in it. Yeah, that's clearly an ultrafilter, right? And that's clearly an ultrafilter. And actually, in this case, it's even true that the intersection overall S in S in U1, sorry. Maybe let me write it like this: S with a property S is in U1. In this case, consists clearly of one point, right? Namely 3, right? Now let me make, and if you take the fattenings, I let you, I mean, it's very, very easy exercise to see that if you take now the fattenings instead of S, so I take here these constructible sets, then I get P3, right? You know what P3 is, right? I have here P3 plus, and here P3 minus. Okay, so that's good. So another example would be U2, let's say. I take all S in S such that there exists an epsilon bigger than 0, a real epsilon bigger than 0, such that the interval of real numbers between 3 and epsilon lies in is contained in S. Is contained in S. So it's easy to see that this is a filter again. It's actually an ultrafilter, right? By the way, yes, it's actually an ultrafilter. Please do it as an exercise. It's an ultrafilter in this Boolean algebra. Please do it as an exercise. By the way, it wouldn't be an ultrafilter if I took here the interval where the endpoint 3 is included. Oh, sorry, I have to take actually 3 plus epsilon, I'm sorry. So 3 plus epsilon is contained in S. Yeah, that's an ultrafilter, easy to show. And it wouldn't be, by the way, if I included here the 3. Okay? And then now the intersection overall S with S in U2 is actually empty. It's clear, right? But if I take the intersection of our fattenings, it's an easy exercise. It's P3 plus, right? And maybe let me make another example. U3 is the set of all S in S, such that there exists an N in N, such that the interval minus N infinity, doesn't matter if I include minus N or not in the interval, is contained in S. And yeah, again, it's you know, it's an easy exercise to show that this is an ultrafilter again. And now again the intersection over all S, where S is in U3, is empty. But the intersection of our fattenings, easy exercise, is actually P infinity. You know, where P infinity is this prime cone corresponding to the point plus infinity. Yeah, you have also one for minus infinity. Yeah, easy exercise, and I think if you understand this example, then you understand a little better what's going on here. And actually, in all these cases in this example, you easily see that actually this is true, that a prime cone could be described at all as the set of all f in A, such that yeah, you could also say this like f is non-negative on one of the filter, on at least one of the filter sets, right? Okay, so here you say it's the set of all f which are non-negative on 3 actually. Here you say it's the set of all f which are non-negative on a right-sided interval right to 3. And here you say it's the set of all f which are non-negative on a neighborhood of infinity in some sense, right? Okay, good. Okay, in a naive sense, because we didn't introduce this topology, which I'm referring to here. Okay, good. So by lemma 533, there is some Q in the real spectrum of AT, satisfying that the intersection over all these fattenings is exactly Q. Okay, that's because U is an ultrafilter. Now we show that we have to show that Q equals PU, equals this PU which we have defined, right? So these are two inclusions. So from left to right, if F is in PU, then then by the definition of PU, this set where F is non-negative is in the filter, is in the ultrafilter, right? So yeah, and of course it's a semialgebraic subset, and then I can fatten it, and yes, and by this thing here, I know that Q is an element of it, right? Because this fattening contributes here to this intersection. So Q is in this fattening. So now by the definition of fattening, right? What is the fattening of this? Well, I know that's the set of all that's the set of all prime cones in the real spectrum of a pre-ordered ring AT, such that they satisfy also this inequality in some sense. So that means that f head of q is greater than or equal 0, right? So that means f head of q is greater than or equal 0, and hence that means just f in q. So that was the inclusion from left to right. On the other hand, if now the other inclusion I proved by contradiction, so I suppose I have an f which is in A but not in the left-hand side, when I have to show it's not in the right-hand side. So if f is not in pu, then that means, that means that this set is not in U, but U is an ultrafilter. Here I use that U is an ultrafilter. So its complement is in U, but the complement is this, is the set of all x in R to the n, where f of x is smaller than 0, right? And so, so this is in U, and so the fattening of it contributes to this intersection. Therefore, Q is in the fattening of this. That means f head of Q is less than 0, and hence f is not in Q, right? So it was about the same argument, but I needed this step. I needed this step that this, if this is not true here, that then the complement of this set lies in U. Here I needed ultrafilter. Okay, so now we have associated to each ultrafilter in the Boolean algebra of k semialgebraic subsets of R to the n. We have associated a prime cone of a pre-ordered ring AT, where T was this pre-order generated by the non-negative elements of a fixed ordered field K. Right? Okay. Now conversely we can do something converse. So let P be prime cone of real spectrum of AT. Then we can actually find an ultrafilter of semialgebraic subsets, k semialgebraic subsets of R to the n, which seems to have to do with it. And the way we do this is as follows. So I take so one description which is perhaps less surprising is that I take this is a point of real spectrum of AT, right? So this immediately gives rise to an ultrafilter on the constructible subsets, on the Boolean algebra of constructible subsets of this real spectrum of AT, right? That's clear, right? A point gives rise to an ultrafilter. I said once that ultrafilter is a generalization of a point, right? But here it really corresponds to this point. So I get an ultrafilter on the Boolean algebra of constructible subsets of real spectrum of AT. But this Boolean algebra is isomorphic to the Boolean algebra of k semialgebraic subsets of R to the n, we know, right? And this is actually by the slimming. So I could say that so maybe I write actually something. So first I could look at the ultrafilter of constructible subsets of real spectrum of AT, which contain P. It's an ultrafilter in curly C. And then it's clear by the isomorphism of Boolean algebras, it's clear that I get here another ultrafilter of a set of all. I could could say like this, I could slim the C's, right? And that's an ultrafilter in S. Sorry. Or I could say I take Vs in S such that P lies in the fattening of S. Right? This is again an ultrafilter in S. So in this way, I have associated to this point in the real spectrum of AT, I've associated an ultrafilter, which I call the ultrafilter an ultrafilter in S. And now I could define the UP in this way. Well, I actually want another description which does not use this slimming and fattening, right? I want somehow more explicit description, doesn't use this very abstract operation slimming and fattening. Exactly like here, you know, could have defined the PU in terms of this, but yeah, I mean, this bit complicated because I use this fattening, right? And so I prefer to define it in this very concrete way here. In this very concrete way here. And here the same thing, I want to define the thing in a very concrete way. However, this concrete way looks a little bit complicated here. Okay. So, you know, so the question is how do you do this? And it turns out that this is the right way. You say that you define this ultrafilter UP as the set of all k-semialgebraic subsets of R2Vn, such that such a set, such a k-semialgebraic subsets of R2Vn is contained in S, where F is in the support of P, and where exists finitely many Gi in P without minus P. Okay, so it turns out that this is the right way of doing it. Yes. Okay. So somehow that's, you know, you say that, you could say that take some system of an equation and strict inequalities that's somehow satisfied by the point P, right? I mean, the f head of P is 0, clearly, and G1 head of P is bigger than 0, and so on, right? And take such a thing that is satisfied by P, and this defines a on the other hand a k-semialgebraic subset of R2N, and I say that on this subset that S should contain this subset. So the idea is, maybe let's draw a picture again. So the idea is that maybe let me draw a case of two variables now. So it should be R to the 2. And so you have some point P, you know, and we don't really know how to represent the points P. But we know that we knew from previous chapter that R2 is can be seen as a subset of real spectrum of AT, right? And we don't really know how to draw this. In the case of one variable, if we have just one variable, we know actually how to draw this, right? That was the usual picture like I had just before. So you know that P3 plus sits infinitely close to 3 and so on, right? In the case of two variables, we don't know exactly what can happen exactly, right? But somehow we imagine that sum varies with point P, right? I mean, I don't know. So maybe here you have an actual point. So like, let's say 5, 3. So that's a 0.53, right, in R2. and then maybe somehow there is, you know, in two dimensions I cannot just say to the right of something or to the left of something, right? It's more complicated, and maybe there is some, I don't know, semialgebraic arc going out here or something, whatever this is, and then this and then somewhere here, or maybe it could also sit at infinity, right? We have also this pre-orders at infinity, but maybe somewhere this is, you can imagine that it's somehow like an airplane landing in this point. That could be a and then the question is, how does it land? And is it in a semi-algebraic way? It should be in a semi-algebraic way somehow, on a semi-algebraic curve or something like this. Well, that's just intuition, right? And when I take a semi-algebraic set such that P is in the fattening of S, right? But we know how semi-algebraic sets look like. They are finite unions of such sets. And that will be the reason that this actually works with this description, right? And that's just saying here, I mean, that's condition that f is in the support of P and which are in P without minus P means just that P satisfies in some sense this system of equations and inequalities, this system of an equation and inequalities. And the reason why we take just one equation is because we can afford, right? Otherwise you could also take several ones, that's also okay. For inequalities we cannot afford this problem. Okay, good, so proof is actually not long, so let's prove it. Okay, so since set of all constructible subsets of a real spectrum of AT that contain P is clearly an ultrafilter in C, and the slimming is an isomorphism of Boolean algebras, the set of all S in S where P is in the fattening of S is an ultrafilter in S. I had already said this. From a description of K-semi-algebraic subsets of R to N implied by theorem 186, I already said this actually. Where is it? It's here somewhere. Exactly. Right? Here we had it even for K-semi-algebraic classes, but then in particular for sets. Good. One gets that this ultrafilter equals so I'm speaking about this ultrafilter here, equals the set of all S in S such that P is, what I did here is just something very complicated. I wrote down, I said, instead of saying, I use that S is a finite union of such sets. And since the condition is that P is in the fattening of S, I could also say that P is in the fattening of one of these sets contributing to the union, because the fattening is an isomorphism of Boolean algebras. And when I'm just saying explicitly that there should be such a one of these sets contributing to a representation of S as a union of such sets, so that there is such a representation such that S prime is this, right? Yeah, so easy exercise is just a complicated way using this 186 complicated way of writing everything. And but when I'm done, because what does it mean that P is in the fattening of S prime? Well, it means exactly that f head of P is 0. That means F is in the support of P. It means that Gi head of P is bigger, and Gi head of P bigger than 0 means that Gi is in Pi without minus Pi. Yes. And this ultrafilter is UP, and it equals this. So everything okay. So now we come to Brocker's ultrafilter theorem. The correspondence, on the one hand, an ultrafilter in S, in a Boolean algebra of k-semialgebraic subsets of R2n, is mapped to the corresponding point Pu in the real spectrum of AT, right? That was just the prime cone of all polynomials that are non-negative on one of the filter sets, or you could equivalently say whose non-negativity set is in the filter, is in the ultrafilter. And on the other hand, I take a prime cone containing T, so I take an element of a real spectrum of AT, and I map it to this UP just defined. This defines a bijection between a set of ultrafilters in S and the real spectrum of AT, right? And yes, so now maybe this gives really a good intuition of what is, well, it's certainly not a very good description yet, we don't have maybe, but it's already a very good intuition what is an element in the real spectrum, right? Okay, so it's very geometric already, although the problem is that ultrafilters can be very complicated to know what ultrafilters exist, right? Not easy to, many ultrafilters are not easy to write down or cannot be written down explicitly, maybe. Okay, so maybe let's illustrate this. So now for n equal 1 and r equal k equal r, we know exactly what is the real spectrum, right, of this polynomial ring in one variable over the reals. Pre-order does not play any role here because the non-negative elements of r are squared, right? Are squares. So, but already for n equal 2, we don't have a good description, and still I cannot give one, right? But of course, this gives nevertheless a lot of insight, right? So here you say that you can describe it by an ultrafilter of semialgebraic subsets of R2. Now it's not easy to, most ultrafilters are not really easy to describe, but at least you can gain some intuition about it, right? Okay, so one set, if I look at the semialgebraic subsets of a plane of R2, right? One set is always, no matter what ultrafilter I'm looking at, one set is always in there, right? That's this one, that's R2, right? So I know already that if f is non-negative, if a polynomial f is non-negative on R2, if it's globally non-negative, when it's non-negative on a filter set, and then I know that for the corresponding prime cone, it lies in the corresponding prime cone, right? Because this is always a filter set, I know that all globally non-negative elements, all globally non-negative polynomials lie in every prime cone, right? You could have proven this in another way also, it's not completely trivial, right? Okay. And then, but now let's look more closely. What ultrafilter do we have? So how could one find out? I mean, not really, but conceptually. You take now any semialgebraic subset of a plane, like for example with disk, right? And when I know that either the disk or its complement, right, are a filter set. So now it depends on the filter, of course. So let's say the complement is a filter set. So we are here with a complement, right? Complement of a disk. But now you can take another semialgebraic subset. I don't know, you can take a half plane, for example, right? So let's take this half plane. And we know that either the intersection with the half plane or its complement, or the intersection with the complement, lies again in the filter, right? So that means, so let's say maybe we take the half plane. We have fine half plane. We have a blue region here. So when we are now, what we keep now is this. So what we have to delete now is this. And also this. Right? So now I have a smaller set. And so on, right? Now I can take another semialgebraic set. Well, it could look more complicated also, right? Like this one. Or its complement, right? Okay. Now maybe it's again the green region, so depending on the filter. Let's say it's the green thing. Okay. So we are staying with this thing here, right? And so you can imagine like it's a semi-algebraic set getting smaller and smaller, right? And then, it could either the part that remains when time evolves, right? It could be more and more far from so it could move there towards infinity somehow, right? So that you're really moving outside there, for example, right? Or maybe or maybe, you know, maybe in the next step you delete perhaps this here, right? So it's like a semi-algebraic set getting smaller and smaller. And maybe in the next step you delete this, and then this, you know, like now you have perhaps, now it looks like perhaps like this, I don't know. And so on, right? Something getting smaller and smaller, right? And when the condition is that polynomial f is somehow at some point of time when this semi-algebraic set gets smaller and smaller when time evolves, and at some point of time your polynomial is just non-negative, right? On this semi-algebraic piece getting smaller and smaller, right? So that's a bit to intuition, right? Still it's a complicated story, right? So okay, so yeah, so let's prove it now. I think we have now good intuition, and now let's prove it. So to show we have to show the following things. So we have to show if U is an ultrafilter in S. So we know already the well-definedness of both maps, right? We know already the well-definedness of both maps, but by the two lemmata. But if U is an ultrafilter in S, when we go here and when we go back, so we have to show it that when we come again to U. So U equals U PU. On the other hand, if P is in the real spectrum of IT, we have to show that P equals PUP. Okay? P equals PUP. Okay. So in order to show A, let U be an ultrafilter in S. So we have this characterization of U. We have this characterization of UPU, right? So I mean that was 535. That was a characterization of some UP, right? Actually use a more abstract one. It's more abstract, but it's easier to argue with. So we use this red characterization here. Okay. So we have to show here that instead of P, I'm just taking here PU. So we have to show this, right? And okay, so but since the fattening is an isomorphism of Boolean algebras, we have that set of all S in S such that PU is in fattening of S is a filter in S. You know, because if I took here a fattening of S instead of S, then I would of course have a filter of a Boolean algebra of constructible sets in the real spectrum of AT, which is defined by one of the points in the real spectrum of AT. Okay, so this is a filter in S. And since U, I mean, we have seen this many times actually. Since U is maximal filter in S, right? U is a maximal filter in S. Confer 5.1. Ultrafilters are exactly the maximal filters. 5.1, 15, right? So that was this thing here. Okay. Okay, so since U is a maximal filter in S, it suffices to show that U is contained in this, right? Because this is a filter, and U is a maximal filter. If I want to show them to be equal, which I have to show, then it's enough to show this inclusion, right? So again, 5.1.15 was really okay. We did this really in Boolean algebras. filter in Boolean algebras. Okay. Good. Okay, we have to show U is contained in this. Well, to this end, let S in curly U. And we have to show PU is in a fattening of S. But by 534, you know, with fattening of S is one of the sets in the intersections in 534, the other lemma, right? So actually this lemma here. Yeah, I could also, yes, that's actually the lemma we use here. So PU is in the fattening of S for each S in U, right? Okay. So this could also say this singleton is contained in the fattening of S. And thus PU is in the fattening of S, of course, right? Okay, so that's it. So all these abstract things led quite automatically to what we wanted. Okay, so and B, if P is in the real spectrum of IT, then you have to show P equals PUP. Let P be in the real spectrum of IT. So by 534 again, the intersection consists of exactly one element, namely PUP. Therefore, it is enough to show that that P is this unique element, which is in the intersection. Okay. Was fix S in UP, and we have to show that P is in a fattening of S. But this is by 535 again. Since S is in UP, we see here that this means that P is in a fattening of S. So it's also automatic. It's just really abstract, but it's almost automatical. Everything is automatical here. Okay, so that's the main theorem of this section, I guess, but we want to give some applications. We want to show it's really useful, right? And for this, we first need a proposition which is completely on the side of the semi-algebraic sets. So, and later we will think about what is a consequence for prime cones. Okay, so every semi-algebraic subset of R to the n. So remember that k less than or equal was an ordered field. And R was its real closure. Right? Okay, so and every semi-algebraic subset of R to the n, right? That is semi-algebraic subset means R semi-algebraic subset, so it's defined by polynomials with coefficients from R, is even K semi-algebraic. That means it's even defined by polynomials with coefficients over K. Right? So let's see. So to begin with, we show that all one-element subsets of R, so all singleton subsets of R are K semi-algebraic. So that's of course because R is being the real closure of K together with less than or equal, when it's of course because R is algebraic over K. Right? For this, let A be in R. To show that the singleton set with A is K semi-algebraic, we have to show this when R over K is algebraic, so there is a polynomial, a non-zero polynomial over K in one variable actually, sorry, it's here just in one variable. we are starting here actually with a case n equal 1 and with very special sets, right? Namely singletons. So I have a polynomial in one variable, so I have to correct this in the lecture notes. With f of a equals 0, so you could take, for example, the minimum polynomial over k, and then set k to be the number of roots of this minimum polynomial f over r, and so it's at least 1, right? So because a is such a root. And choose j in 1 to k such that a is the jth root of k when the roots of f in R are arranged in increasing order, right? Of course, I don't count the multiplicity of the roots. Okay. And they are arranged in increasing order with respect to the order, the unique order of a real closed field. By applying the real quantifier elimination 1/817k times, we obtain that the followings that the singleton set A is indeed k semialgebraic. Namely, I can define it with quantifiers by saying it's the set of all y in R, such that there exist k elements from R, which are, such that x1 is less than x2, x2 is less than x3, and so on. And all xi are roots of f, and xj is y. Right? So this can be written down with k quantifiers. So quantifiers are ranging over real closed field. These are polynomial inequalities, right? So x1 less than or equal x2 is a polynomial inequality, and so on and so on. So I'm here actually doing, I'm actually applying the real quantifier elimination 1/817 in the setting where we had an ordered field k. So that's actually real quantifier elimination even for classes. And the setup there was sufficiently general because it's written here. Here it was, right? In the sequel, we let kp always be an ordered field, for example. R a set of real closed fields containing kp as an ordered subfield. So we don't even need here that R is real closure or is algebraic over k. Just need that it's real closed. Yeah, so now consider an arbitrary polynomial in n variables, and it suffices to show that the set of all x in R to the n such that p of x is non-negative is k semialgebraic, right? Because these sets here, now I'm back in n variables, and these sets here generate, these sets here, which I highlight in yellow, these sets here generate, right, where p is a polynomial with coefficients in R in n variables. These sets generate the Boolean algebra of all semialgebraic subsets of R to the n, right? Semialgebraic, so R semialgebraic if you want. So write p like this. So a coefficient, so d is the degree of p. If p is the zero polynomial, then it's minus infinity, and then this is the empty sum. But the A alphas are in R, my real closed field, but all singleton sets A alpha, they are k semialgebraic by what has already been shown. We can actually write down this set in a k semialgebraic way. namely quantifier elimination yields that so I want to write down this in a k-semialgebraic way, and by quantifier elimination I'm allowed to take finitely many quantifiers over elements of real closed field R. And these were only finitely many of these coefficients, so I have here a family of for each coefficient of p I have here a real I have here an element of real closed field with finitely many existential quantifiers actually I take, and I just say that these y alphas equals the a alphas. And since this is k-semialgebraic, I'm allowed to write this here. Effectively, I write y alpha equals a alpha. Okay. I mean, the reason why I did not just write y alpha equals a alpha, but because when you think, he wants to write down a polynomial inequality, but he uses for corresponding polynomial would have coefficients which are not in k. So since I have already shown that I can express with this condition being in the singleton set using k-semialgebraic polynomials, using polynomials over k when that's okay, right? So this is just a polynomial inequality, right? Okay. And instead of the existential quantifiers, I could in fact also take universal quantifiers in the same. That wouldn't matter actually, right? It would express exactly the same thing, because here it's just written right, y alpha equals a alpha. So if you want, you can also put universal quantifiers here. Good, now let's apply this to what is the consequence what is the consequence of this proposition 537 if you look at for real spectra, right? Because this says about this says that the Boolean algebra of k-semialgebraic subsets of R to Vn is the Boolean algebra of semialgebraic subsets of R to Vn. Is really literally the same. And these things appear in Brecker's ultrafilter theorem. It appears in the usual Brecker's ultrafilter theorem like it is written here, where k equals, where R is the real closure of k less than or equal, right? But I could apply Brecker's ultrafilter theorem also in the situation where, let's say this is a blue situation, where I take, instead of the ordered field k less than or equal, I take R itself, right? So that's so I take R less than or equal R, because this R is its own real closure, of course, right? Okay, so when this S here has the same meaning in the orange and the blue version of a theorem, right? Just because the k-semialgebraic subsets of R to Vn are the R semialgebraic subsets of R to Vn, when the Boolean algebra of these subsets is always the same, no matter whether I'm in this or in this situation, right? So So here I have bijection. I have two sides. I have here a prime cone side, and here I have the ultrafilter side. And so I can go from the, I can take the blue version of a theorem and can take a prime cone in the polynomial ring over R, go back, get an ultrafilter in S, which is always the same, no matter whether I mean the blue or the orange S, but so I actually come to the, since I'm applying a blue version of a theorem, right? So I get from the polynomial ring over R, from a prime cone in the polynomial ring over R, I get an ultrafilter in the blue S, which is the orange S, and when I go back, right, and I get a prime cone in the polynomial ring over K, right? And that's a bijection. That's a bijection. So from a prime cone in a polynomial ring over R, I get the prime cone in a polynomial ring over K, which contains the preorder T, which contains the non-negative elements of K, of a ordered field K less than or equal, and this is a bijection, right? So it seems that I have kind of a nice map from the real spectrum of Rx to the real spectrum of AT, which is a bijection, right? Now, we know already some canonical map from here to here, of course, the restriction, right? That's certainly the map we would think of first. And now we have just to check that the map that is induced by these two applications of Brocker's ultrafilter theorem is exactly this natural map. One would guess, of course, right? But let's verify it. And when we get that this map is bijective, right? And that doesn't seem obvious, right? It's probably non-trivial because it says that you can extend every prime cone here, every point in this real spectrum of AT is the intersection of prime cone of Rx with A. Doesn't seem to be trivial, right? So you can lift it somehow. That's the surjectivity, and the injectivity also doesn't seem to be immediate, right? Because so that means that this lifting is actually unique. I guess it's not really obvious, right? Okay, so, and we get it now for free from a preceding proposition, from this one, together with Brocker's ultrafilter theorem. So let's see. So let's just almost for free, because we still have to check that this bijection is the one we would guess it is. Yeah, but because of Brocker's ultrafilter, or because of the preceding proposition, we obtained from applying the ultrafilter theorem of Brocker twice, once in a special case where K equals R. That so what did I do here? I mean, I said I start here with an element of this real spectrum, and okay, I chose to do it like this. So I apply the blue theorem, the blue version of a theorem, which is in this situation where K equals R. And I don't use the lower line. The lower line, maybe I could use it also, but I just ignore it. I use the upper bijection, and the inverse of that, which would be the lower line, is that PU maps to U, right? So I write the inverse map here in this way. So PU maps to U in the blue setting, and when I map it back to PU in the orange setting, right? So now what was PU? PU was this thing here, right? Pu is the set of all polynomials such that that are non-negative on a filter set. So I said I start with a blue version, so I have to take first polynomials over Rx, set of all polynomials over R, so that the non-negativity set is in a filter. And I map it to the orange Pu. So when I have in the orange version, I have to take all polynomials over K, right? But this set is still taken over R, right? Yes, looks a bit complicated, but you see here, I mean, the thing is just that this condition is, of course, the same exactly as this condition. It's just that once I look at all polynomials over R and once over K. And so it's clear that, that this is exactly this map, right? Good. Good, let's now draw a corollary. So instead of a polynomial ring, I take a field of rational functions in n variables over R. And here the same. Instead, this was a polynomial ring over K in n variables. Here I take the field of rational functions in n variables over K. And that was a pre-order generated by the non-negative elements of the ordered field K inside the polynomial ring. And here I take the pre-order generated by the same elements in the field of rational functions. And the map otherwise is defined by the same rule here. And is again bijective. So that's a statement about ordered fields, right? Instead of real rings. So the elements of a real spectrum of a field are just orders, right? So prime cones are the same as orders. So, well, let's look at this commutative diagram. So I have here the map that I'm interested in. So this is the map from which I claim that it is bijective, and that's exactly this map here, right? And then I have the downward arrows. These are okay, so when I look at this map here, okay, maybe let me draw this in blue. So this map here, from which I know already that it is bijective, right? This somehow has to do with this map here, right? You see. Except what is new here is that what I highlight now in yellow, but here I take only those which are of support zero ideal. But still this is a well-defined map. If I start here with a prime cone of this polynomial ring whose support is with zero ideal, it is mapped here, of course, again to such a prime cone whose support is with zero ideal. Okay. And then I have here the two downward maps are also very natural. That's also just restrictions, right? Just intersection, here with Rx and here with A. That maps actually into this thing. With yellow conditions here are satisfied for the images here, right? Because, you know, the support of a prime cone is the zero ideal here, because this is a field and this is a field. I mean, prime cones are orders in fields, right? And support of an order is always the zero ideal. Okay, good. And this diagram is commutative, obviously, right? It's always just restriction. I mean, it's just intersection with, it doesn't matter if I map this way or this way. And both vertical arrows represent bijections, right? So that's actually not true, I think, in the way I wrote it up here. So I have to write here AT. Otherwise, it would be very surprising in general, right? Okay, so I wouldn't have search activity probably. But everything what I said is also okay if I write here AT. But now when it comes down to proving that this is a bijection, then I guess I really need this. I mean, so... And okay, let's maybe first look at this arrow here. Let's first say that this is a bijection. I do this by proposition 3, 3, 4. Okay, so what does that mean? That means that you could do it by hand somehow, but let's look at 3, 3, 4. 3, 3, 4 was something much more general. It was about localization, right? So what I have here now is I have an integral domain, and so here I have an integral domain, and S is multiplicative set A without 0, right? And when I see that there is a bijection between so what does that mean? That means then that the support of P is just consists just of 0, right? Because its intersection with A without 0 is empty. Okay. And this is actually just a quotient field of A. S2 minus 1A is a quotient field of A, right? And yes, and this, this is just A intersected Q here, right? So you see that the bijection I've been speaking of is actually just given by this here. And that's, of course, the inverse map. Okay, and you see that yes, I guess, yes, you see also here that so that shows already the first vertical arrow is that this one is a bijection. And for the second one now, the problem is that I have this additional pre-order, but so here I have AT and here I have this pre-order. But that's just meaning I'm filtering out those prime cones that contain with non-negative elements of K, and that's a fixed subset of my integral domain, which in this case is A, right? And the maps, where was it? So 3, 3, 4. Yeah, so if I have here a fixed subset of A, right? Then I could here write here the condition that P contains this fixed subset of A, and here also could add such a condition. So this is preserved in both ways by this mapping, right? Okay. Easy to show. Can do it everything directly if you want to have a little more work. Okay. So these are bijections, right? And I want to show that this is a bijection. Well, then it's enough to show that this is a bijection, right? But without the yellow conditions here, we would have showed this. That's what, in fact, we have showed here, right? So the only thing that remains to show is, okay, that even with a yellow condition, that's still a bijection. Well, injectivity is, of course, inherited from a case without the yellow part here. But surjectivity is the only thing we have to think about, right? So in fact, we have to think about that if you have some P here, that when it's pre-image under the bijection, which I have already without the yellow condition, its pre-image has also support 0, right? Yeah, so that's, I think this requires a little bit of work. I don't think that's immediate. So because of a bijection from 538, it therefore suffices to show that every P in the real spectrum with support of P has not, so I do the contraposition. I start with something which has here not the 0 ideal as support. And we have to show that if I intersect it with A, right, it still has not the 0 ideal as support. So let P be in the real spectrum of this polynomial ring over R, and let F be an element in the support, which I call now fractal P, which, and suppose F is not a 0 polynomial. So the problem is that F might not be a polynomial with coefficients from K, otherwise I would be immediately done. Now the idea is to produce out of F one with coefficients from K. Namely, I take an extension field L over K containing all coefficients of F, but being finite over K. And actually not only finite, but a finite Galois extension, right? So, in fact, I could just take, I mean, that must not be a subfield of R, right? But it's a subfield of algebraic closure of K. So I just take the splitting field of this polynomial F over K, for example, right? So I join the coefficients of F, but also their conjugates in the Galois theoretic sense, right? So that I get actually here a normal extension, and I have anyway a separate extension then, because separable extension, because I'm characteristic 0. So that's a little bit of Galois theory, right? A tiny little bit. So we had this already, you should know this from your Introduction to Algebra course, and we used already much more Galois theory when we do here, actually, in the proof of a generalized fundamental theorem of algebra. Okay, in one of the previous chapters. Okay, so I take this Galois extension, that finite Galois extension over K, that contains all the coefficients of F, right? As I said, L is not necessarily contained in R, but it's contained in the algebraic closure of K. By extending the action of a Galois group from L to L adjoint X, right? So, I mean, you know, you can just apply it coefficient-wise to polynomials. You can apply a field automorphism of L that fixes K point-wise, coefficient-wise to polynomials, right? So with G times F actually means, so G is such an automorphism, means that I apply G coefficient-wise to F. When I get another polynomial over L now, And when I take a product overall G, overall with automorphisms G, there are only finitely many. And yeah, and the resulting polynomial, if I take the product overall with polynomials, must have coefficients over k, because it's invariant under the action, right? So it's coefficient-wise invariant under the action. So by Galois theory, it has coefficients in k. And therefore, it's a polynomial over k, so it lies in A. But it's still not a zero polynomial, because product of non-zero polynomials is a non-zero polynomial. I'm working here with polynomials over fields, so that is a valid argument. And so, what remains to show is that only that H lies in the support of P intersected with A, but that means H lies in fracture P intersected A. Now here I said that this would be obvious, but thinking a bit about it, I don't believe it anymore. So I mean, it's very easy to show, but I wouldn't say it's obvious. Namely, what's the point here? I mean, the idea is that P is okay, that H lies in A, that we have just shown, right? But the idea why it lies in P is that H is a multiple of F, right? F lies in P, and H is a multiple of F, so H lies in P. Okay, but that's not a valid line of argumentation, see, because H has coefficients, H has coefficients over K, right? But you know, here from this I see only that H is a multiple of F in the polynomial ring over L, right? Remember that F, the coefficients of F were originally in R, but I included them also in L. And all these GF have also coefficients over L. So H is a multiple of F over L. That means in a polynomial ring over L, right? Good. So, but P is an ideal in a polynomial ring over R, right? So how do I get that H lies in P then? Okay, F and H, they lie both in L adjoint X, right? And yes, but P is not an ideal over, so fracture P is actually an ideal in R adjoint X. Okay, so, and the situation is as follows. So we might actually, you know, both. So if you denote the algebraic closure of R by C, right, then this is also the algebraic closure of K, and L, of course, is algebraic over K. So without loss of generality, L is also a subset, a subfield of C, right? And now I'm actually intersecting. So it's actually much more complicated than it seems here in the lecture notes. So I can intersect R with L. I think I have to look at this field, this intersection field, right? So now I know that, you know, because here F is multiplied with some other polynomials over L, and I get H. So I know that F divides H in L adjoint X, right? And now, yes, so, you know, F lies actually, F has all its coefficients actually in R intersected L, right? Because the coefficients of F lie in R, right? We lie in R, and but also in L by construction of L. So F has its coefficients here in R intersected L, and H has its coefficients, well, actually in K even, right? So in particular also in R intersected L, right? So actually F and H are both polynomials in R intersected L adjoint X. Now I claim that F divides H even over this field. And that's an argument of, well, you can prove it in several ways, but one, maybe the easiest argument is via linear algebra. Namely, you can express this divisibility as the solution of a linear system of equations. Let me explain this. So, an affine linear system of linear equations. So, you know that this is divisible means that there is a G, so there exists, okay, let me have a blue version first. There exists a G over L such that F times G equals H, right? And I know what degrees what is the degree for G that I need, right? Because, you know, for example, if a degree of H is 10 and the one of F is 7, then I know that G is of degree at most 3, actually exactly 3, right? So, but I can write that there is a polynomial of degree at most 3, right? And so I can just write G as, you know, in this way, A alpha x to the alpha, right? And I can read this polynomial identity here as if I expand on both sides and I compare coefficients, then I can read this as a system of affine linear equations in the A alpha that is solvable because this G exists, right? It's a system of affine linear equations that is solvable. And the coefficients of these systems are from L, right? And it's solvable over L, right? And now, but actually, the coefficients are actually over R intersected L, and it's solvable in L, right? So it's if a linear system of equations is solvable in a bigger field, right? When it's also solvable in the original field, because deciding solvability is, for example, via a Gauss algorithm. And Gauss algorithm is the same no matter if you stay in the smaller field or you go into the bigger, right? So and therefore this system of linear equations is also solvable over R intersected L. So there are B alphas or alpha. So there is a G hat in R intersected L satisfying the same thing, right? Because there are some A alpha tilde not hat. And yeah, so that's the argument. So in the lecture notes, I really have to write more about this, obviously, because it's not that obvious actually. So I will do this, I will correct this in the lecture notes. So this is not obvious. Let's maybe for now, let's just write non-obviously. Now let's come to the last theorem of this section. That's the following one. So let L together with less than or equal prime be an ordered extension field of K less than or equal. When we have again this map, the restriction map, so I intersect a prime cone with a prime cone of the polynomial ring over L with a polynomial ring over K. And since this was an ordered field extension, I get, of course, here a prime cone that contains the negative elements of K, because that one should have contained the non-negative elements of L, right? So here I look at this pre-ordered ring. I look only at those prime cones. So here the points of this here are those prime cones of a polynomial ring over L that contain the non-negative elements from L. Yes, so in some sense the situation is quite similar to the theorem we had above, to theorem 538. Maybe let's compare. So where we had, where R was the real closure of K less than or equal. So that's now much more general. We have actually an arbitrary ordered extension field and not this very particular one. Note that L over K need also not be algebraic, and L need not be real closed, does not need to be real closed. So it's really an arbitrary ordered extension field where here it was a very particular one, right? But the map was the same. Right, so I mean here I didn't need to specify that the prime cones should contain the non-negative elements of R, because that was automatically, because in R every non-negative element is a square. So it was really the same map as here. But here I claim bijectivity, and here I claim only search activity. Right, so guess it's not surprising that you cannot hope for. It's not surprising that you cannot hope for injectivity here, yes. Okay. So and the second difference is that the proof of this was really easy using the ultrafilter theorem. Here we will give a proof again with your ultrafilter theorem, but it will be more involved. Okay. So, okay, new page. Okay. So let S curly S prime prime denote a Boolean algebra of all L semi-algebraic subsets of R prime to the N, where R prime is now a real closure of this ordered field. So maybe let me make a diagram here. So we have here K together with less than or equal. That's an ordered subfield of L together with less than or equal prime. And here I have a real closure R prime. So this is real closed. And this is an algebraic extension here. It's an extension of ordered fields also. So a Boolean algebra of L semi-algebraic subsets of R to the N, right? So coefficients are from here, but the subset is contained in a subset of R prime to the N. Good. When I look at and by the way, we know that the ultrafilters in this Boolean algebra correspond to the real spectrum of a polynomial ring over L, right? By the ultrafilter theorem. And the Boolean algebra, so maybe let's write this. So S prime prime closely related to, by Brücker's ultrafilter theorem, to the real spectrum of this polynomial ring over L. And when I look also at the Boolean algebra S prime of k semi-algebraic subsets of R prime to the n, right? So these are the L semi-algebraic subsets. And when I have S prime is the same thing, but now k semi-algebraic subsets. And here I think I don't have, so that was not a situation, the Boolean algebra S prime is not directly concerned by the ultrafilter theorem of Brücker. Because you know, R prime over K, for example, doesn't even have to be algebraic. In the ultrafilter theorem, I had this very particular situation where I looked at the real closed field, which was actually the real closure of the ordered field over which where my polynomials had coefficients in. Okay. But this Boolean algebra, of course, is trivially contained in that one, right? Good. But this Boolean algebra S prime is isomorphic to S, which was all the time the Boolean algebra of k semi-algebraic subsets of R to the n, where R is the real closure. So if here of k less than or equal, so I have here R real closed and algebraic over k. And it should be an ordered extension field of k less than or equal. That means R is the real closure of this ordered field. And R prime is the one of this, right? Good. Now, these are two real closed fields. R and R prime are real closed fields, and they have this common ordered subfield k less than or equal. In this situation, the transfer works. The transfer between k semi-algebraic sets, right? So maybe I should. So this is k semi-algebraic. So S, by the way, the ultrafilters on S corresponded to the real spectrum of of K joint X. I forgot, by the way, here that I should take a pre-order. Above, I forgot this, I'm sorry. Here I need a pre-order. So the order on L was less than or equal prime, yes. So and here I need k greater than or equal. Sorry, greater than or equal, of course, not less than or equal. Okay. So now I think it's okay. So the ultrafilters on S prime prime correspond by Brücker's ultrafilter theorem. The ultrafilters on in S prime prime, correspond by Brücker's ultrafilter theorem to the points of this real spectrum of this preordered ring. and the same here with S and this real spectrum. Okay. Now I have this transfer between semialgebraic, k-semialgebraic sets, subsets of R to the n and R prime to the n. That was 195. Maybe let's look at this again. Yes, it was here, right? This was this transfer, and yeah, that was really, I mean, here, you know, in section 1.9 there was really no other hypothesis. So Kp was an ordered field, and we looked at real closed extension fields of Kp. It was not necessary that they are algebraic or something over K. So everything should be okay. So we have this transfer, and in virtue of this transfer, because this is an isomorphism of Boolean algebras, the Boolean algebra S prime, right, is isomorphic to S, right? So here I have, you know, S prime was subsets of R prime to the n. Maybe I should indicate this. K semi-algebraic ones. S prime prime was L semi-algebraic subsets of R prime to the n, and S was K semi-algebraic subsets of R. And so this is so S and S prime are isomorphic as Boolean algebras. Let me write it like this. Okay. They are isomorphic. Good. Now let Q in the real spectrum of AT be given. So A was actually, if you remember, A was polynomial ring over K. And T was this. Right? Now let Q be in the real spectrum of AT be given. And we show that there is a P in the real spectrum of this preordered ring, that when I intersect it with A gives back Q. Good. So that's what we have to show. Good. So that means I need to. I can start here with an ultrafilter Q in this algebra, right? And I need an ultrafilter here, finally. So let's start by Brücker's ultrafilter theorem. So by 535, Brücker's ultrafilter theorem, UQ is an ultrafilter in S, right? And now, how do I come from here to here somehow, right? In some nice way. So first, I can go by means of this transfer. I can go to here, right? So that resolves a problem that that my filter sets should be subsets of R prime to n. So that's already okay. The problem is that I'm still in the wrong Boolean algebra, because I'm looking at a Boolean algebra of just K semi-algebraic subsets, and that's not the one which can be connected to this real spectrum by Brücker's ultrafilter theorem. So I need somehow to go to an ultrafilter consisting of L semialgebraic subsets. But since UQ is a filter in S, actually an ultrafilter, but I don't care anymore, in fact. I get here, so I go now. In some sense, I do what I said. So I go first here, and then I get from the ultrafilter here. I get at least a filter here. That's the basic idea. I get a filter here from the ultrafilter here. I get a filter here, but these two steps going from here to here, and then getting at least still a filter here. That's combined in this one single step here. So a curly F is the set of all S prime prime in curly S prime prime, such that there exists an S in UQ, such the transfer of R to R prime of S is contained in S prime prime, right? So that's a trick to get from an ultrafilter here a filter here. Okay, so that's a nice trick. So you can immediately verify that this is a filter, right? So I guess that's a very easy exercise. Now, but I need an ultrafilter, so because I can extend a filter in a Boolean algebra to an ultrafilter in the same Boolean algebra by 5.1.16. Maybe let's look at it again. Right, it's this thing here. I get with Brecker's ultrafilter theorem, now I'm here, and then with Brecker's ultrafilter theorem I can go here, so I get a P in the real spectrum here, such that U equals UP. So we have that Q is PUQ by Brecker's ultrafilter theorem. And by the definition of this PU, that's a set of all F in A, set of all F in A such that the non-negativity set of F is a filter set. That means it's an element of UQ. And now I apply the transfer. So if you want, I go here in this algebra, and I take the corresponding filter here. The ultrafilter of SUQ corresponds to an ultrafilter here, and that's explicitly written here. I don't give it a name. And then I have the condition becomes, of course, that this transfer is an element of that. So that's trivial by the property of a transfer, that it is an isomorphism of Boolean algebras. And now here comes some equality with an exclamation mark. So we think about that later. So I claim that this is a set of all F in A such that this set here, so the solution set now in R prime to the n instead of R to the n of the same polynomial inequality is an element of U, right? Where U was this ultrafilter chosen in S prime prime. So we think about that later. But once you accept this, then this is by the definition of Brecker's ultra filter theorem. That's PU. I mean, if I wrote here a polynomial ring over L instead of K, when that would be exactly PU, you know. U is an ultrafilter here, so to that there corresponds a prime com PU here. But since I write here F in A, that's just intersected with A. So this is with prime con intersected with A. But U is UP, and I have a choice of P, and so this is PUP intersected A. But PUP is P, right? By the ultrafilter theorem. So that's P intersected A. So and when I'm done, right? So the only thing that remains to show is the exclamation mark. So I should have said where less than or equal prime is of course the unique order on R prime. Sorry, that's of course, I mean that was, what else should it be, right? I should tell this. And the equality flagged with an exclamation mark follows from the following claim. Namely, the claim is that U intersected S prime is exactly this set that appears here, right? So once I've proven this claim, then I'm clearly done, because what I highlight here in blue is actually, of course, exactly this, right? So this transfer, of course, can be written like this, and so if I have here that this yellow set is equal to U intersected S prime, then I can clearly write here U intersected S prime, right? But S prime was the Boolean algebra of K semialgebraic subsets of R prime to n, and that is such a subset, right? So that this is an element of S prime is anyway trivially true, so I can forget about that here. Good. So what remains to show is this, and here there is one trivial direction and one non-trivial direction. The direction from right to left, yes, inclusion from right to left is clearly trivial, because so UQ was an ultrafilter in the Boolean algebra S, so the elements of S are all K semialgebraic, so that this set is contained in S prime is clear, and that it is contained in U is also clear, because it's actually even contained in F, right? Because for each such set, for each such transfer, you can choose here, if you have a transfer of some S here, then you can choose for the same S here, and this is actually satisfied with equality here, right? Good, so that's trivial. So the other direction from left to right follows from. There is a from missing here. Follows from effect. From effect. So that this is an ultrafilter. That that's an ultrafilter in the Boolean algebra is prime, obviously, since UQ is an ultrafilter in S, and thus it's a maximal filter in S prime. Maximal and ultra is the same, right? Maybe let's see this again. So that was this proposition. And so everything I have to show is that U intersected S prime is a filter in S prime, right? And that that's actually trivial, right? Just verify axiom by axiom. Everything is trivial. Okay, so that was it for today. Thanks for listening. Next time we go to section 5.4 about the finiteness theorem for semialgebraic classes. And many thanks for listening, and goodbye. See you next time.